All right, so let's dive into something kind of fun today.
Abstract algebra. No, before you panic.
We're going to make this as painless as possible, I promise.
You sent over some fascinating excerpts from the online encyclopedia of integer sequences.
The OEIS,
Okay.
specifically entry A00001.
Never heard of it.
Oh, yeah. The OEIS is amazing. It's like this treasure trove.
The fascinating number
Yeah,
sequences.
and this one in particular, A00001.
Deals with counting groups.
Okay, so maybe we need a little less abstract and a bit more, explain it like I'm 5.
What exactly is a group in this context?
You got it. Imagine you have a set of objects.
It could be anything. Numbers.
Yeah.
Even those books on your shelf.
A group is a way to combine those objects according to specific rules.
Okay, I'm picturing my bookshelf right now.
So how do these group rules work?
One key rule is that you need a way to combine any two objects in the set.
And get another object that's also in the set.
Think of it like a recipe. 2 ingredients in.
One delicious result out.
And
That result has to be part of your original set of ingredients.
interesting. So it's not just about combining things.
It's about how those combinations interact within a closed system.
Or set, I guess.
Exactly. And to be a group,
There are a few more rules these combinations need to follow.
for example,
There has to be a special identity object that doesn't change anything when you combine it with other objects.
like,
Adding 0 to a number doesn't change the number.
right,
Makes sense, is that all?
because this is already bending my brain a bit.
Almost. You also need every object to have an inverse.
That means for every combination you do,
There's a way to undo it and get back to the original object.
think about adding and subtracting the same number.
Okay,
I'm starting to get it.
but back to this OEIS thing.
Where do the numbers come in?
We're counting something about these groups, right?
You got it. The OEIS sequence you asked about
A 00001.
tells us how many different groups exist for each possible size.
So, for
There's
example,
only one way to make a group with just one element.
no matter what that element is,
So it's like if you only have one book on your shelf,
there's only one way to arrange it.
it's already in the only possible order.
Exactly. But as you add more elements,
Things get interesting fast.
with 2 elements,
There's still only one possible group.
but with 3 elements,
There's only one unique way to arrange them as a group.
and so on.
Wait, hold on.
I'm already getting a little lost.
This is where I usually start looking for the easy button.
That's completely understandable.
Yeah.
What's fascinating is that this sequence
How many groups exist for each size?
gets really complex really quickly.
That's what caught my eye. The first few numbers in the sequence are 1,
1.
1, 2.
It seems straightforward enough.
But then it explodes. Why the sudden jump in complexity?
It all comes down to prime numbers
Yeah.
and how they interact to form larger numbers.
Remember how we talked about group structure?
Yeah, those recipe rules for combining elements.
Right. Prime numbers, it's 5, 5.
It can only be divided by 1 and themselves. They're like the building blocks of numbers.
And it turns out
If a group size is a prime number,
there's only one way to structure it.
so a group of 7 elements is straightforward because 7 is a prime number.
Exactly. But when you start looking at groups with sizes that are products of prime numbers,
Those are called composite numbers.
the number of possible structures skyrockets.
Okay, let's break this down for our listener.
So if you have a group of, say, 12 elements,
That's 2 times 3.
that's a lot more complicated than a group of 7, right?
Absolutely. Think of it like building with Legos.
If you only have one type of brick,
Your options are limited,
but give someone a mix of different bricks,
and the possibilities explode.
and the more types of bricks or prime factors you throw into the mix,
The more intricate those possibilities become.
that actually makes a lot of sense.
So how does the OEIS sequence actually account for all this complexity?
Well, the OEIS sequence isn't just a random list of numbers.
It's the product of serious mathematical research.
The entry you provided has a ton of links to research papers,
Obvious.
even computer programs dedicated to understanding this complexity.
So it's like a digital detective board for math nerds
Exactly. And there's even a formula,
to calculate the number of groups for some specific cases,
though it's not exactly light reading,
even for relatively simple cases.
where you're dealing with a prime number raised to a power.
The formula gets surprisingly intricate.
Can you give us a taste of that complexity?
I'm dying to see what has mathematicians so stumped.
Sure. Let's say you're looking at groups with a size of 8. 8 is 2 raised to the power of 3.
The formula to calculate the number of possible groups gets pretty wild.
Involving things like greatest common divisors and combinatorial functions.
Okay, you lost me at combinatorial functions.
But the point is it gets complicated fast,
Even
right?
for what seems like a relatively small number.
Precisely. And this complexity highlights why the OEIS sequence is so fascinating.
It's not just about memorizing a list of numbers.
It's about grappling with the incredible diversity of structures.
That can emerge as you consider larger and larger groups.
You know, when I first saw this sequence,
I thought, okay, it's just some math thing,
interesting to a few people,
but not really relevant to my life.
but the sheer volume of research around this suggests otherwise.
Is there more to this than meets the eye?
Oh, absolutely. This isn't just some mathematical curiosity.
Understanding groups is fundamental to countless areas of study.
Like what? Give us the example.
Take cryptography, for example.
The security of many online transactions relies heavily on the properties of certain groups.
Wait, you're saying that my online shopping habit?
Is secretly governed by these abstract mathematical structures
In a way, yes. It's these complex group structures.
that make it difficult for hackers to crack encryption codes.
Mind blown.
Okay, what else?
Well, have you ever wondered how physicists describe the fundamental symmetries of the universe?
I'll admit that's not my usual dinner table conversation.
But you've got my attention.
Well, groups are essential for that, too.
They help us understand things like the behavior of subatomic particles and the laws of motion.
Okay, I'm starting to see the bigger picture here.
But I have to ask,
What about something a little closer to home?
does this group theory stuff have any implications for...
Say the average music lover.
As a matter of fact, it does.
Group theory is used to understand musical scales and chord progressions.
The relationships between different notes and chords can actually be represented using
That's it.
groups.
Wow, I had no idea my Spotify playlist was hiding such mathematical depths.
This is blowing my mind.
And there's even more. Remember how we talked about the sequence representing the number of subgroups within a larger group?
Yeah, the whole groups within groups idea.
Like a mathematical nesting doll.
Precisely. Well, this connection hints at a deeper relationship.
Between seemingly different areas of mathematics.
For instance, the number of groups of a certain size,
Also pops up in other areas, like topology,
the study of shapes and spaces.
and even number theory.
So it's like this sequence is a secret passageway.
Connecting different rooms in the vast mansion of mathematics.
Exactly. And what makes it even more fascinating?
Is that it's full of surprises.
Like what?
Don't leave us hanging.
Oh, one surprising fact I stumbled upon in the OEIS entry.
Was a reference to a 2020 work by Desmond McHale.
He showed that for some sizes,
There are actually more groups than rings.
which are another fundamental algebraic structure.
Wait, hold on.
More groups than rings. That sounds counterintuitive.
Aren't they both supposed to be these fundamental building blocks of math?
That's what makes it so interesting.
It's these kinds of unexpected results that keep mathematicians up at night.
It just goes to show how much we still don't know about these seemingly simple structures.
This is incredible. It really makes you wonder what other mathematical mysteries are lurking out there.
Speaking of mysteries,
There was one more thing in the OEIS entry that caught my eye.
a conjecture by someone named Jorge R.F.F. Lopes.
Ah, yes. Conjectures are like unsolved puzzles in the world of mathematics.
They're educated guesses that seem plausible based on evidence.
But they haven't been rigorously proven yet.
So this Lopes fellow, what's his conjecture all about?
His conjecture suggests there might be a kind of multiplicative property to this sequence we've been discussing.
He proposes that if you multiply the number of groups of two different sizes,
It'll always be less than or equal to the number of groups of the size you get by multiplying those original two sizes together.
okay, you've officially lost me in the weeds of mathematical jargon.
Can we get an example up in here?
Of course. Let's say you have a group of size 4 and another group of size 3.
Lopes' conjecture suggests that if you multiply the number of possible groups of size 4,
By the number of possible groups of size 3.
the result will be less than or equal to the number of possible groups of size 12.
Because 4 times 3 is 12?
Okay, I'm following so far.
But why does this conjecture even matter?
What's the bigger picture here?
That's the million-dollar question, isn't it?
If Lopes is right,
It suggests there's a hidden structure governing how the number of groups grows as their size increases.
it would be like finding a secret formula.
That unlocks a deeper understanding of these fundamental mathematical objects.
So it's like finding a hidden pattern in a seemingly random sequence of numbers.
And that pattern could potentially unlock a whole new level of understanding about groups.
And maybe even other areas of math.
Exactly. It's like finding a hidden doorway in a vast library.
Who knows what other secrets we might uncover by stepping through it?
This whole deep dive has been an incredible journey.
We started with a simple question about counting groups.
Something that let's be honest, sounds a bit dry at first glance.
And stumbled into this fascinating world of hidden patterns
Unexpected connections.
and mind-blowing implications.
It's a great reminder that even in the seemingly abstract world of mathematics,
There's always something new to discover.
something that can surprise us
Challenge our assumptions.
and ultimately deepen our understanding of the universe and our place in it.
And who knows, maybe one of our listeners will be the one to finally prove or disprove Lopes' conjecture.
Adding another piece to the puzzle of A00001.
If you're up for the challenge, you can find all the resources you need linked in the show notes.
Until next time, keep those minds curious and those questions coming.